Previously, we talked about conservation of energy a bit when we talked about open and closed systems, but now we're going to get much more precise and technical and be very clear, and then we'll do some examples. So jumping into that, conservation of energy says that the total amount of energy in a process is constant. It doesn't change. So whatever the total amount is, it's constant. So it may change form, in other words, go from one energy system into another, or it may be transformed, which is just another way of saying that. It may change form or be transferred, which is another way of saying that. So it can go from one energy system into another. It can also change form, but it cannot be created or destroyed. However much you had, that's how much you have. I'm going to put a slight asterisk on this and say there are ways to technically create or destroy energy, but they obey larger conservation laws. If you want to talk more about that, let me know in class and I'll answer it. But the total amount of energy is constant. It can't be created or destroyed. For at least for our class, that's a good enough model. Regardless, if you want to think about the more kind of accurate view, there's a bigger category of things that energy is part of, and that bigger category is constant. So it's kind of like an even fancier version of changing systems. So for a closed energy system, the total change in energy, in other words, the sigma delta E is equal to 0. This is what we talked about in the last video. Because there's no energy going in or out, all of the changes have to cancel out. But for an open energy system, we can have energy exit or leave. So we can have that happen as heat and work. So the energy will equal the energy added or removed from the system. So if we add energy or if we remove energy, it's coming from the surroundings, so it's not being created, it's not being destroyed, it's just going to or coming from the surroundings. Let's look at an example here. So a ball falls a total distance of 10 meters. If the ball was released from rest, what is the final speed of the ball? Solve this problem using kinematics and energy considerations and compare your results. So let's do kinematics first, because that's hopefully a little more familiar. And actually, why don't you give this a try and see what you get as a result. All right, if you were thinking about this, you knew that your delta x was equal to 10 meters. Because let me draw a diagram, be a little more precise here. I'm just going to call down positive in this case and up negative, so I don't have to deal with negative signs. We have our initial and our final. V is equal to question mark meters per second. V naught is equal to 0 meters per second. And A equals G equals 9.8 meters per second squared. And that's downward, so it's also going to be positive. So if I have delta x, g, and the v's, I know I want to use this equation here. V squared equals v naught squared plus 2a delta x. So v is equal to plus or minus the square root of, and v naught squared is 0, so plus or minus the square root of 2 g delta x. So v is equal to plus or minus but we know it's going to be positive because it's going to be pointed downwards, so I can actually go straight to just the positive. Square root of 2 times 9.8 meters per second squared times delta x of 10 meters. So that's going to be roughly 100, so roughly 200. So V is about 2 square root 10. Sorry, 10 square root 2. I put those backwards because it's about 100 times 2. So 110 square root 2 meters per second. So now with energy, let's look at the same thing. What objects are involved? We have the ball and the earth. We see that the ball is changing height, so we expect to see a change in gravitational potential energy. We see the ball is changing speed, so we expect to see a change in kinetic energy. And because there's no objects pushing or pulling on that ball except for the earth, and we've included the earth in our system, we know that this is a closed system. So delta UG plus delta KE will equal 0. So delta UG is equal to negative delta KE. Delta UG is mg delta H. Delta KE is 1/2 m delta V squared. So mg, well, actually the m's can go away. And we're left with just g delta H is equal to 1/2 V final squared minus V initial squared, but we know V initial squared is 0. And so we get V is equal to the square root of 2g delta H, which we also know is just delta X from the problem over here, and that, you'll notice, matches right up there. So in other words, we get the same thing in both cases, which is good because there's only one situation, so there should be one answer. That's the idea of conservation of energy. You add up the total changes, set them either equal to 0 or the amount of energy added or removed, and then calculate whatever it is they want you to find. So here's another example. If we consider the falling ball from the previous problem, and in this instance we assume the ball has a mass of 150 grams, that it loses 20 joules of energy as heat because of air resistance, what is the final speed? This we can't easily do with kinematics because it's not in free fall anymore. It's losing energy as heat. That also means that we're going to consider, in this case, I'm going to think of it as an open system, because I'm going to say that 20 joules is just lost. It goes away from the system. So same as before, we're going to take the change in gravitational energy and add the change in kinetic energy. But this time, instead of equaling to 0, we're going to say it equals negative 20 joules because the system loses 20 joules. And because we want the final speed, we need to solve for the delta KE because that's going to have speed in it, and that will equal negative 20 joules minus delta UG. So KE will be 1/2 m times V squared minus V initial squared, which remember V initial squared is 0. And that's going to equal negative 20 joules minus, and then UG delta mg delta H. Now in this case, because we're dealing with gravitational potential energy, we do need to pick up to be positive and down to be negative, because gravitational potential energy gets larger as you go away from the Earth. So I left with 1/2 mv squared equals negative 20 joules minus mg delta H. V is equal to the square root of 2 divided by m times negative 20 joules minus mg times negative, in this case, 10 meters. And let me actually leave that as a delta x for a second so I can do all the substitutions at once. So v is equal to the square root of 2 over 0.15 kilograms times negative 20 joules minus 0.15 kilograms times 9.8 meters per second squared times negative 10 meters because it's going downwards. And at this point, I'll leave it as an exercise for you to actually go in and calculate this, but we should get roughly 150, positive 150. This will be roughly, so v will be approximately square root of 2 over 0.15 kilograms. This should be 100 just about times 0.15 would give us 150 minus 20, so times about 130. So you're going to get something a little bit over the square root of 10, I think. But you can go through and calculate it yourself.